So this exam has the lowest grade boundaries of any high-level paper 2 in this whole iteration of the syllabus, which means it's the hardest one. It is a stinker. 48% of the teachers that filled out the G2 form said too difficult, and it is despairingly difficult. I struggle with a few of these questions. I kind of know what I'm doing as well. All right then, no vaccine. Still for me. All right then, so question 1. How can I monitor the change of iodine concentration? Very few good answers. Well, iodine in solution is either brown or purple, depending on what it's in, and who knows what it's in here, propanone and acid. But the iodide, just like sodium chloride, is colourless, and if you think chloride's going to be colourless, then probably iodide is going to be colourless as well. And so use a colorimeter. That's how you'd follow this reaction. It probably goes from a brown colour to a colourless colour, or at least some kind of colour fading is going on. So a colorimeter, that would get you the point. They would also accept pH, which isn't great because you're making H plus here, but really the question's about the iodine. Next question. Rates of reaction. Well, if I've got concentration and time on my graph, then just the slope of that is the change of concentration of a reactant over the change in time. Well, that's rate, isn't it? So let me draw a line of best fit. And the IB said that few people did draw the line of best fit. And let's just work out the gradient. So rise, that looks like it's going from a 0.8 till 0.35. And how far across is that? Isn't that 60 seconds? 60 seconds. So I'm going to do rise over run. So the rate is the change in concentration of iodine over the change in time, which is 0.8. So 0.0075. And that's going to be moles per decimeter cubed per second. Ooh, looks a bit grim. Let's put per second. Is that good enough for the IB? It is. Anywhere between 0.007, 007 to 008, we've got you that point. Is it just 1 point? Yeah, so what's the second point for? One for the line and one for the number. Didn't need the units. Next question. Mostly well answered. I think this is quite straightforward, isn't it? So if I double the concentration of the acid, then it looks like my rate is doubling. And if I quadruple the concentration of the acid, it looks like my rate is quadrupling. So that's an order of reaction 1, isn't it? If you changed the concentration and nothing happened to the rate, that would be 0. If you change the concentration, say by doubling it and the rate doubles, or tripling it and the rate triples, that's order of reaction 1. And if you double the concentration and the reaction goes up 4 times as fast, and if you triple the concentration, it goes up 9 times as fast. That's order 2, isn't it? So what's the question for me? The relationship, well, it's directly proportional. I double one, the other one doubles. So I would say directly proportional. And the order of reaction is going to be 1. Directly proportional, first order. Oh. Well, hopefully they give me 1 for first. I scratched my head about this the first time I looked at this, but I did it the long way. Here's the short way. So looking at the gradient of these lines, they're essentially equal. So the gradient of the line is the rate. The rate is basically proportional to the gradient. Change of concentration of iodine over change in time. That was the question we just did. Well, as you change the concentration of iodine, the reaction doesn't go any faster. It doesn't go any slower. The rate's the same. So the concentration of iodine has no effect on the rate of reaction because it's constant. The slope of the graph is constant, which must mean iodine has an order of reaction of 0. So iodine's going to have a 0 order. And the reason is because as you change the concentration of the iodine, initial concentration of the iodine, the rate is unchanging. Yeah. Or we can just say the gradient's the same. So there's your 2 points there. 0 order, unchanging gradient. 1D. I don't agree with their model answer for this. I've got another answer. They got me a point now. So this is a strange kind of graph. I'm doing the reaction without acid. Well, that seems reasonable. You're doing it without acid, doesn't it? Going to the equation at the top, it is without acid. It's just iodine and propanone. Anyway, okay, so you're doing it without acid. And it goes really slowly. The gradient is essentially 0. It goes really slowly. And then it gets faster and faster and faster and faster. There's 2 reasons why a reaction goes slow and then suddenly runs away with itself. The first is that reaction gets hotter and hotter and hotter, and then at some stage that becomes a self-perpetuating cycle. The hotter it is, the faster it goes, so the hotter it is, the faster it goes. That isn't the answer they'd accept here. What they want is the second reason, which is that you're producing a catalyst. That as the reaction goes forward, it produces a catalyst, which makes it go faster, which produces more catalyst, which makes it go faster. That's called autocatalysis. And I don't remember them ever asking about it, certainly not on the syllabus. Now you could just describe autocatalysis for that 1 point. And for the second point, you had to say the rate was very slow, and then it increased and got faster and faster and faster. That would be your second point. Question 2. Describe metallic bonding. Well, it wouldn't surprise me if you lost a point on this. I think I would have done. I would have said positive metal ions in a sea of delocalized electrons, expecting my 2 points. But you also have to say there's an electrostatic attraction as well. Electrostatic attraction being the positive ions attract the negative electrons. That's the 2 points there. Now we've got an isotope question. Pretty straightforward. Now you might think, I'm smarter than the IB, I'll just look up on the periodic table they provided the value for titanium and just quote that. Nah, you get 0 points for that. That's specifically told in the mark scheme to give you 0 points for that. You actually have to do the maths. It gives you a number slightly different. So I've got 7.98% of them are 46 plus 7.3. So I've got a 47.92.93. Now they want 2 decimal places. Is that good enough? Yeah. What about units? Well, relative atomic mass has no units, but they could have asked us, what's it relative to? Well, it's relative to carbon-12, which has a mass of 12. Protons, neutrons, electrons. 90% of people got this correct. So the small number is the number of protons, the atomic number. The difference in the number of neutrons, what's that going to be? 26, 36, 46, yep. And the electrons is also the atomic number for this atom. Smashing. You have to get all three right for your point. Okay, the electronic configuration, the full electronic configuration for the titanium 2+. Well, I'm going to do titanium first, and then I'm going to whip off those 2 electrons. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. So that's for titanium. Let's just double check my memory's serving me correctly. Yep, so titanium ends at 3d2. Now for the titanium 2+ ion, you've got to take off 2 electrons. And the 2 electrons that we're going to remove are from the outer shell. The outer shell is that one, the 4th main energy level. So those 2 are gone. Now, what the hell happened there? I filled those up first, and now I'm taking them off first. That's beyond the IB. Don't worry about it. Why is the melting point of vanadium greater than titanium? So let's see. I've got vanadium and titanium. Well, there's kind of 2 IB reasons why melting points of metal change. It depends on how big the metal ion is, and it depends on the charge of that metal ion. So it's to do with charge density. Bigger ions have lower melting points, and lower charged ions have lower melting points. So I think it's probably something to do with the charge density argument. So charge density is proportional to charge over the volume of the ion. And also, if there's got a higher charge density, it's going to have a higher melting point. Now the charges of the ion, the vanadium ion and the titanium ion, well, they have multiple charges. Both can be 2+, titanium can be 4+, vanadium can be 5+. So I'm thinking it probably isn't going to be the charge of the ion, because you wouldn't be expected to know that. But I do think the volume of the ion is important. So looking at the trend in radius, francium is the biggest atom on the periodic table, Fat Frank, that's how I think about it. And helium is the smallest atom. So following that pattern, vanadium must be smaller than titanium because it's closer to helium. So if vanadium is smaller than titanium, that means the charge density is higher and the melting point is higher. So I think that's the reason. Vanadium has a smaller ionic radius. Yes. Is it only 1 point? Yeah, okay. So this convoluted explanation of charge density wasn't needed. All you needed to say was that vanadium has a smaller ionic radius. Okay, next one. We're looking at vanadium. So let me just write out the electronic configuration for that. 1s2, 2p6. All right, well, that's how the electrons, I'm going to move this over to there, just to remind myself that the 4s electrons come off, or ionized, first. So removing electrons one by one by one, like pulling the petals off of a flower, that's how I think about it. Removing them one by one is always increasingly difficult or requires more energy. And the reason is you're putting the electrons off of an increasingly positive ion. The first electron comes off of a neutral atom, second electron comes off of a +1 ion, third electron comes off of a +2 ion, and there's increasing electrostatic attraction. So whatever the pattern is, the pattern's going to be increasing. So it's definitely going that direction. But I think it's going to be more sophisticated than that. The first 2 electrons come off quite easily. They're in the valence shell. The next 3 electrons, well, it's tempting to say the next 3 electrons are going to take a lot more energy to come off. After all, they're from the 3rd shell, where the first 2 are from the 4th shell. But no, that's not true. The 4s and the 3d are very close in energy. In fact, they actually swap places occasionally. They're so close. So the first 5 electrons are going to come off with just a nice increasing step-by-step pattern. But the 6th electron, which would come off from the 3p, that is quite a long way energetically from the first 5. So the last electron to come off is going to have a high jump. So I'm going to have 6 in a relatively straight line. Sorry, 5 in a relatively straight line, and the last one's going to be up higher, like that. So that would give me my points. And it's only 1 point. So I think one of the problems with this exam is that that was a lot of work for 1 point. Why an aluminium alloy is harder than pure aluminium? Well, there's kind of a default answer for this, is that if you have metal ions of a pure metal, I'm not going to put the charges or the sea of electrons in, what can happen is when you tap that side, you can move these ions along and they'll move along like that. Well, that makes sense. But if I was to add another ion in there, if I was to add a different ion in there, maybe an ion here or a bigger ion there or some ions like that, then if I tried to tap and shift along that top row, it would be blocked. By adding these extra foreign ions in, the lattice is now not so neat and you can't shift the rows as easily as you once could. So their answer was it prevents the layers from sliding over each other for 1 point because the atoms or the ions are different sizes. Okay, so that's fair enough. So the first point was the ions are different sizes. And the second point was prevents the layers from slipping. Slipping so easily, I think. All right, 2 points for that. E. So ligands. So just to refresh your memory, if I have, for example, copper 2+ ion, and then I have some water coming in as a ligand, it's kind of a classic example, then one of the lone pairs on the ligand will perform a dative covalent bond or make a dative covalent bond with the central transition metal ion. So the bond between a ligand, is it just dative covalent bond? Is that going to be enough? A pair of electrons provided by the ligands do not accept dative or coordinate bonding alone. Oh. See, normally if an exam is this hard, they'd be more flexible with their answers. I think my answer's fine. But they won't accept it. You need to say a pair of electrons are provided by the ligand. A pair of electrons provided by the ligand. Okay. Dative covalent bond was not enough. So why do transition metals form coloured compounds? For 4 points. In my mind, that's a bit of a lazy question. They have 4 points to fill. What are we going to do? Oh, we'll just throw that out. Okay, so let's try to explain it, see if I'll get my 4 points. So imagine for 1 point, you'd have to say that you have a partially filled d orbital. So maybe I'll partially fill it just with those 2 electrons. Then the ligands come along and cause a split in that d orbital. I expect that's a 2nd point. The third point is that if you shine a visible light, Roy G. Biv, then one of the electrons from the lower energy part of the d orbital will be promoted to the higher energy part. And when that electron is promoted, one or more of the wavelength of visible light will be removed. So the light's gone through, and let's say the green light has been absorbed. And the color that you then see from the complex is the complementary color of the light that's been absorbed. Let's see if that's my 4 points. Partially filled d orbitals. Ligands cause the d orbitals to split. Light is absorbed as an electron choke goes to a higher energy level. Energy gap corresponds to light in the visible region of the spectrum. I think we probably got that. Color observed is the complementary color. All right. So I think I give myself those 4 points. Next up. State the type of bonding in potassium chloride. So it's a metal and a non-metal. Metals hate electrons. Non-metals love electrons. So the electrons are going to be transferred. So the answer, I would say, is ionic bonding. But with this exam, who knows what they've given us the answer? Ionic bonding resulting in electrostatic attraction. Who knows? Yeah, they'll give you ionic bonding. Oh, thanks. So that's for 1 point. Next, 4G. Only a handful dare to believe. What could cause titanium chloride, a metal and a non-metal, so probably ionic, to have such a really low melting point? Melt in your hand. So it can't be ionic bonding, can it? But it must be, because it's a metal and a non-metal. Well, you're going to have to dare to believe that titanium tetrachloride is actually covalent. And I don't know what shape or anything about it, other than I would imagine it's probably a tetrahedron, isn't it? Titanium tetrachloride, that just feels weird. So it's covalently bonded, which means that the intermolecular force between one molecule and the next is probably London dispersion forces, since the dipoles cancel. So this has London dispersion forces, a weak intermolecular force. Potassium chloride is ionic, which has ionic bonds, which is a very strong, you could argue, intermolecular force. And so that accounts for the elevated melting point. Is that enough for my 2 points? So this is a simple molecule, simple molecular structure, which has weaker intermolecular bonds. They didn't ask, you didn't have to specify what the weaker intermolecular bonds were between the molecules. Okay, except specific examples, such as London. So if you said this was covalent molecule, this was a covalently bonded molecule, they wouldn't give you the point. Because, of course, when you're melting titanium tetrachloride, you're splitting up one TiCl4 from another TiCl4. You're not actually pulling apart the titanium and the chlorine. You're not actually breaking those covalent bonds when you melt it. So the fact it's covalently bonded wasn't actually required. Is this question going to end? No. Okay, H. Titanium tetrachloride reacts with water to form titanium 4 oxide. So Ti, and that's 4 plus, and O is 2 minus, crisscross method, Ti2O4, cancel that down to TiO2. Okay, titanium 4 oxide, TiO2. Oh, well, there must be another thing that's made, because that hydrogen can't just be hanging out there. So I've accounted for the titanium and I've accounted for the oxygen. I haven't accounted for the hydrogen or the chlorine. So I suppose that makes HCl. Let's try to balance that. 2 there. 4. Does it want state symbols? No. So let's have a look. Nice. State symbols were not required. So what's the disadvantage of using this smoke in the enclosed space? Well, if you're making hydrogen chloride gas, actually maybe even hydrochloric acid, because there's water present, that's going to be corrosive to your lungs, cause you to tear up. After all, it's a low pH substance. Is that enough? Breathing, respiratory problems, it's an irritant. They'll give you it's toxic. That seems such a broad thing. Your best guess was it's toxic. Normally they wouldn't give you a point for that, but this time they did. Okay, that's question 2 finished. I have to take a day off between these questions. So my hair has doubled in length since you last saw me. Just one question a day on this most evil paper. Okay, a new day, a new question. Question 3. This is awful. I think this might be my least favourite IB question. So much work to get 1 point. If you spent the time to get this question right, you're out of time for the rest of the exam. But if you got it right, you're a 7 student. What a disaster. All right, okay, oxidation states first of all. So the sum of the oxidation states equals the charge on whatever you're talking about. Oxygen in a compound is -2, set for peroxide, which gives me vanadium as +5 +5 and +4. All right? Yeah, okay. If you put 5+ or 4+, you'd lose a point because that's how charges are written. Oxidation states are written +5 +4. Okay, different shirt, same teacher. Let's carry on. So for 3B, I like to consult the standard electropotential table just to get my head straight around this. So at the top of the metals hate electrons, and they seem to have negative E cell values. At the bottom, well, I see fluorine. I know that fluorine loves electrons and has a positive E cell value. So let me annotate this table a little bit here. I know that those hate electrons, and I know that these love electrons. So let's think of the metals. Metals hate electrons, so they want to undergo oxidation, because oxidation is loss of electrons. So that means that they're reducing agents. A reducing agent is itself oxidized. Looking down to the chlorine, that loves electrons. So something that loves electrons wants to undergo reduction. Reduction is gain of electrons. And so that means they're oxidizing agents. I think of the little song, an oxidizing agent is itself reduced. Chlorine wants to be reduced, so it's an oxidizing agent. So 3Bi. I want to turn this chemical into that chemical, but I don't then want to turn that V3+ into V2+. So I just want to have one of those half equations happen. I don't want to have the second one happen, because in the question it says V3+ and no further. Well, if I want to get this equation to undergo reduction, because that's what it says in the question, reduction, I'm going to need a reducing agent. So the reducing agents are the ones towards the top of the table. Now, a reducing agent with an E cell value of less than 0.34 will actually work. So which reducing agents have a value of less than 0.34? They're contenders. Well, I've got these 3. But the question says Don't go any further. Don't turn it into vanadium 2+. So I better make sure that my reducing agent won't kick off that next equation. So it has to have a value between 0.34 and minus 0.26. So that's going to be that gone. So it's just these two. The problem with the zinc is that it's got such a negative number, it's such a good reducing agent, it would push the equation down those 2 steps to make V2+. Don't want that. We're not done for my 1 point. Now what is it? Is it the lead 2+ or the lead or the sulfate or the sulfurous acid? Which one of these is the reducing agent, which is itself oxidized? Oxidation is loss of electrons, so which one is losing electrons? Well, it looks clear to me that the lead is losing those 2 electrons and the sulfurous acid is losing 2 electrons. So it's lead and sulfurous acid. Either of those 2 is the answer to that question. Wow, I don't think I've ever worked that hard for a point. This might be the 3rd time I've said this in this video. Next up, difficult. Yeah, it was difficult, what they said. So let me tidy up my chart here. So they're saying they want to turn VO2 1+, VO2, they want to turn that chemical into that chemical. So that means they want to go through that equation to make that, and then that equation to make that, and then that equation to make that. What a mess. So they want all 3 of those equations to happen. Now what are they talking about? Reduction or oxidation? Let's have a look. Let me fill out the oxidation states. So that's going to be +2. That's going to be +5. So we're still talking about reduction. So if we're still talking about reduction, because +5 to +2 is reduction, we're going to need a reducing agent. So once again, we're looking at the reducing agents, the more negative values at the top of the table. So it has to have a value that's more negative than that. If it's more negative than that, it can push it down to here. Then it has to be more negative than that to push it down to there. And it has to be more negative than that to get it to happen there. Whoa. So I need a value that is more negative than all of those. So that's going to be zinc. So zinc is such a powerful reducing agent, it has the most negative E cell, that it can force all of these equations to undergo reduction. Now again, is it zinc or is it zinc 2+? So we're looking at zinc as a reducing agent. Reducing agent is itself oxidized. Oxidation is loss. So what wants to lose electrons? Well, it's going to be zinc wants to lose 2 electrons. So the answer for the next one is zinc. Is it? Yeah. 3CI. Well, initially I thought this was another evil question, but actually it's just an SL level question tied up in a bit of a knot. So we're going to take 2 of these half equations and just combine them. The question refers to this chemical, and then it talks about some acid, and then it talks about that, and then it talks about that and that. So that's a clue that you want to be combining those 2 equations. Right. So I think flip the most negative. Whichever of the equations has the most negative E cell, I'm going to flip it around. So I'm going to flip this one. Now what do I mean by flipping? Well, I'll show you. So I'm going to put the V2+ on that side, and I'm going to put the V3+ on that side with its electron. Now I'm just going to add in the other equation, this one here. Fill that in, VO2 plus 2H plus an electron. And then on the other side, I've got, some more V3 plus and some water. I'm going to tidy that up. I'm going to delete those two electrons, one on each side. If there wasn't the same amount of electrons on each side, then I'd have to double or triple to get them to balance. And I think I can probably combine those two vanadium 3 pluses to make that. Is that right? Yeah. 3CII. Okay, so there's something about spontaneity and delta G. So there's an equation that links delta G to the voltage in batteries. There's the equation. So N is the number of electrons that I cancelled out in that equation when I was making it from the two half equations. It turns out I cancelled out one electron from each side. So N is 1. F is Faraday's constant, which you used to have to memorize, but now it's given for you. 9.65 times 10 to the 4, what was the units? Coulombs per mole. And then the E cell value. So how do you work out the voltage of this battery? Well, teachers have different ways of doing it, but for me, I think find the difference, make it positive. Well, that's for a battery that works. If it's a non-spontaneous battery, find the difference, make it negative. So find the difference, make it positive, that's going to be plus 0.6 volts. Little tip, if you put the volt in, what the hell's going to happen with all the cancelling of the units? It's going to be kind of ugly. So a volt is actually a joule per coulomb. Let's do the mathematics. All right, so that's going to give me minus 57900. And what are the units going to be? Well, I've got my coulombs cancelling, and that just leaves me with joules per mole. Okay, joules per mole. What units do they want? It doesn't say. In fact, you could give the kilojoules or the joules. They'd accept either number. Of course, I think their answer's wrong, because their answer is that I think we're locked into two significant figures by this voltage, whereas their answer has 3. I don't like their answer. Have we got all our points? No, because you have to comment on the spontaneity. So delta G theta is negative, which means it's a spontaneous reaction. Spontaneous. Does that mean if I just make it and look at it, it will happen? Nope. It might be really slow. Or you might have to kick it off with some energy to get it over the activation energy hump. Set fire to it. I don't know. That was awful.